Chapter 14, Programming. I'm sure you're probably saying to yourself, why do we have programming in this course? I mean, CMIT100, are they going to teach us how to program? Well, no, we're not. We're actually going to look at very little real programming during this chapter. But the purpose of this is to describe what programming actually is. There could be a lot of disinformation about it. It takes many different forms. So we're going to look at its different forms, and we're going to see how it's applicable to many areas within information technology. So who does the programming? Well, programmers, aka software developers, that's a field under IT in its own right. I mean, you can be a software developer, and that is your job every day. You come in, you sling code. Nothing wrong with that. That tends to fall more into the field of computer science versus information technology, but there's a lot of overlap there. What about system administrators? What about infrastructure people? Well, we're not developers generally, but that said, there's many cases when we need to understand programming concepts. Right? It might be because you have to maintain programs, maintain applications, especially ones that were developed by an in-house programming shop. And you need to understand how that code works in order to design infrastructure solutions for it to run and for it to deliver its application. Also, there's many times where as system administrators we have error-prone or repetitious tasks that we will write a little shell script around to automate for us. Well, what's a shell script, you say? Hang on to that. We're going to talk about it. So we can look at programming in we're looking at it from a 10,000-foot view here. And we can break it into two halves. We have low-level languages, and we have high-level languages. What are languages? Languages are the syntax, the language that we use to communicate with the computer. And you've probably seen a lot of high-level languages. Those are common, right? These are the languages that you got to take going through our course. Languages like C, C++, C#, Visual Basic, Java is a high-level language. High-level languages tend to have an English-like syntax or a human-like syntax. Now, this doesn't mean that they're not difficult. It doesn't mean that there's not going to be a learning curve there. Lots of concepts to get through with high-level languages. But they tend to be more in a human, presentable type of language. But if you remember, going back to our chapter on numbering systems, computers don't think in that, though, do they? What do computers see? Zeros and ones, on or off. That's the native language of a central processor unit. Well, that is actually a language, and it's called machine language. Kind of see an example of it right here off to the left. Just a bunch of zeros and ones. Good for the computer, not so good for the human beings. So after machine language was developed, oh, by the way, initially when computers were first invented back in the 40s, going into the 50s, machine language was how they were programmed. It didn't take computer scientists long to figure out they needed a better way. So they came up with something called assembly language. All right? Assembly language, and here's an example of it right in the middle column, is still a low-level language. It's higher level than machine language, but still requires a very in-depth knowledge of how that processor works. So it's abstracting some of the operations behind comments like load, store, skip, jump, that type of thing, but it's still very, very low compared to the high-level languages. As we already said, machine language is binary, 0 and 1. There's your two possible values. It is a native language of the computer, of any computer, and it is very specific to the processor. So an Intel x64 processor has a different type of machine language than a RISC processor from Sun Microsystems, for example. Again, because this is nothing but zeros and ones, dealing at the most fundamental level of the hardware, machine language is very difficult for humans to digest. And that's where the higher level languages come in. Languages exist because of these things called language translators. And the name means exactly what it does. It translates from a high-level language or a higher-level language, including assembly code. Take a closer look at that here in a second. All the way from the high-level languages like C and Visual Basic and all that, and turns that code into the zeros and one machine language of a given type of CPU. So translators, these what performs a translation. Now there's really three types of them that we need to concern ourselves with. The first is what's called an assembler. And assemblers are very low level. They go between assembly language and machine language. And we already said assembly language is very, very low level. What about the high level languages? Well, we have two for that. We have a type of translator called a compiler, and another type called an interpreter. So what's the difference? They both do basically the same thing. They move from a human readable high level language all the way down to machine code. The thing about compilers is they do it all at once, which means you sit there in your IDE, your integrated development environment, more than likely, and you're thunking away on your C# code, and you think your program is done, so you will compile it, and the compiler will go through and take all of your code, all 10,000 lines of it, 100,000 lines of it, however big it happens to be, and convert that all to machine language at one time. Contrast that to an interpreter. An interpreter, and this is for a language like, let's say, Perl, where you write your code in the human readable form, but then the interpreter converts it from that high-level language to machine language one line at a time as the program runs. Well, this has connotations for us. Compiled code, once it's compiled, and the compilation process can sometimes take quite a while, runs faster, right? Because it's already in that native machine language. However, it's a little more difficult to work with. If I have a syntax error in my code or a logic error, and it's not doing what I think it should be doing, I'm going to go through the trouble of compiling it, and then I have to test it. And if I realize, oh, I've got to change that, I go back to my high-level code, make the change, compile it again, test it again. Find something else. Compile it again, test it again. Lather, rinse, and repeat. Interpreters run slower because they are translating the code one line at a time as it runs, but it tends to be more dynamic. So when I see a syntax or a logic error, I just stop, change the code, rerun the program, the interpreter kicks in and starts moving it one line at a time again. What's better? What are we supposed to use? It all depends what you're doing, right? What's a better tool, a hammer or a screwdriver? Are you driving nails, or are you trying to sink screws? Assemblers, that's in the realm of your computer scientist people. These are people who are working with assembly code. And they're out there. There's people who have to write the code for microwave ovens and refrigerators and other smart appliances around any of our houses. Those are very high-end programmers that must learn to a very deep degree the architecture of those processor chips and then write an assembly to get it to do what they expect it to do. Run timers and all that kind of stuff. Compilers are generally used by software developers creating a finished product. So if you're on a software development team and you're being paid to write some accounting application for a company, let's say, you're going to produce, more than likely, a compiled piece of code when you're done, a deliverable that can just install and run on a system. Interpreted languages, like things like Perl and shell scripting, remember that? Those tend to be used by IT people, system administrators. When we're automating our tasks, we tend to do it using interpreted code. And we already looked at this. Compiled languages, C, C++, C Sharp, all that stuff. Interpreted language, shell scripts, within Linux and Unix environments. Windows batch files. Anyone remember doing those? Remember the old DOS batch files, which is nothing but a text file with a bunch of commands in it that is executable? Interpreted. And entire programming languages have been built around an interpreted translator. For example, Perl, which actually has a very much of a C++ syntax, but is meant for infrastructure work or for the back end of web development. Sometimes the old CGI stuff was written in Perl. Closer look at assembly language itself. Again, higher level than machine language. This is better than zeros and ones, but it is still considered very low level. And it's considered that because it is so processor specific. Again, easier than for humans to understand. I mean, we can read it, load, store, subtract, jump, so forth. But it is still challenging. It still requires a very intimate knowledge of the given processor. However, assembly, there's not a big jump from assembly down to machine code, which means that code written in assembly tends to be very, very efficient. It can run very fast. High-level languages, and I listed a few of them. Here's some old ones. How about Fortran? Right, that and COBOL. These languages date back from the 50s. So high-level languages came about very quickly after the development of computers. And this is a little example of some syntax right here. This is actually C code, which is fairly low level for a high-level language, if that makes any sense. But we got little lines here. We're declaring some variables, integer variables. We have a little while loop that runs in a circle until some condition equals true. And then we're displaying some output to the screen right here. So again, it's much more understandable for us, but there's still a learning curve. You still have to learn this stuff. Now, of the high-level languages, we can subdivide those into a couple categories. Originally, high-level languages were called structured, or considered structured languages. They tended to be sequential, right? Line 10 does something, line 15 does something, line 20 does something, and so forth. And nothing wrong with that. Even a lot of our fundamental languages like C that are still used quite a bit today, a lot of Windows is written in C, is structured. The recent trend in the last 20-25 years, though, has been more towards object-oriented languages. So languages like C++ and Java and C Sharp and all that, they, instead of dealing with structures, they deal with software objects. So a particular window within a program, let's say, could be considered an object. And you define that object, and then you write code to perform things or do things to that object. Rather than just starting from one sequence of events and ending with another, object-oriented is much more fluid. It has a different look to it. Another development in recent years is what we've called visual programming. Now, I'm going to do a programming demo here at the very end of the lecture. We're going to be looking at a little bit of Linux shell scripting. Just very quickly, look at a couple shell scripts. And we're going to see that there's not a whole lot, it's not very impressive to look at, right? We're using a command line interface inside of Linux editors, and you just type code, and there you go. Well, dating back to the 90s, we saw the rise of things like Visual Basic, right, from Microsoft, which eventually became Visual Studio and .NET. These are visual programming languages. They're object-oriented, but you can see the objects. You can draw the windows on the screen, for example. You have buttons you drag over and radio buttons and dials and all this other stuff that you lay out visually, and then you create code that makes those objects do things. That kind of environment is called an integrated development environment, or an IDE. And they're not just limited to the Microsoft products. There are many IDEs out there. There's IDEs for Java, there's even IDEs I believe out there for Perl, right? There's quite a few of them. Now, I said this isn't a programming chapter. It certainly isn't. And we're not even specific to any particular language. But there's various programming concepts that are relevant to pretty much any programming languages. So we're just going to kind of look at a few of them here. In very basic terms, we have input-output statements. Right? These are statements that either output something to the screen, some result, or to a printer, or to some other piece of code, or it brings them in, either from a user typing on the keyboard, from opening a file somewhere, whatever. So we have I/O statements. Then we have selection statements, and we're kind of looking at some examples of them right here off to the right. Again, this is our C code, but we're looking at an if or an if-then loop right here. So it's conditional. It looks at conditions, and if some condition is true, then do this. Otherwise, do this. And that's the type of logic that allows our programs to be able to make decisions, to have some kind of intelligence built into them. There's also iteration statements. Well, very commonly, most of the time, really, you're not just doing something one time, but you're doing it for a certain number of times, or until some condition is true, or until some condition is not true. Well, we have to iterate to do that. An example of that would be like a while loop, right? While x is greater than y, do this, and there'd be some code in here that would maybe subtract the value from x. And then when x is no longer larger than y, it breaks out of the loop. And again, we're not looking at specific syntax here. The syntax to do this in C is way different than it is from Visual Basic or from Java or from Perl or whatever. But the point is that the types of statements exist in most programming languages. Another thing that's very common is something that's known as subroutines. These are, depending on the language, these may be known as functions. And the point is just this. If I have a program and it's one line after another, I could very quickly get thousands or tens of thousands of lines, right? My programs could get ginormous. Well, ginormous programs are problematic. They're difficult to run. They're resource intensive. They could be extremely difficult to fix if something's not right, if something's broken on them. It's a lot more efficient to work with smaller pieces of code. And that's what subroutines are. And this is a very simple example of one right here. And again, this is looking at a C example. And we have two parts here. We have the main part of the program and this, well, rather lame little subroutine called foo, F00, or FOO. Why did they pick that? I don't know, but they did. So let's look at this. Under the main part of the program, and this is actually the main part of the program right here, you declare it, what part of the program you're in. And really what this is doing is it's displaying this to the screen. It's printing a little hello world statement and says, hey, we're about to enter this subroutine called foo. And then right here, it invokes the subroutine called foo. It's calling it. When it does that, here's what it's calling, right? Which in turn runs this little print statement to the screen. Once this code is completed, control reverts back to the main part of the program, puts another print statement out, and then the program ends. Not a very practical example, but it gives you some idea what's going on there. This allows for code to be modular. Maybe I have 15 programs that could make use of this particular subroutine. Well, I just write it one time and it goes in my toolbox. And I can use it any number of times in different programming jobs. It allows us to pre-build pieces of code, modular programming. Now, I mentioned earlier on, first part of the lecture, about scripting languages. If you're a sysadmin, this is probably where you're going to be. Now, scripting languages have certain things in common. For one, they're interpreted, right? So they get run one line at a time, and they get translated one line at a time. Which means they tend to run a little bit slower, but they're a lot easier to maintain, and it works well for what we're doing. Why do we even write these? Why would we care? Well, let's say you're a Linux admin, and all of a sudden you're tasked with adding 500 or 1,000 users to your Linux systems. Sounds far-fetched, but it happens. Mergers, acquisitions, that kind of thing. Well, if you did that manually, you'll be there for days. Typing. We're human beings, so we tend to fat finger things. We make errors. So not every user account is going to be created properly. We might fat finger some passwords, whatever. A more efficient thing to do would be to write a little shell script. And here's an example of one right here. And we're going to look at a couple more here in a second. That just does it for me. And maybe I'll have just a text file that has all my usernames, and then my shell script will read that text file and add all those users. Every one of them will be exactly the same. And it can be done much quicker than doing them manually. Now, generally, there aren't fancy integrated development environments for scripting languages, although there are some for languages like Perl. Generally, though, we're in a very rudimentary system. We're on a command line, either in a Windows command line or a Linux command line, and we are editing these as straight text files. Right? Think of it as cracking open Notepad under Windows, typing some code, hitting save, and there you go. Now, these shell scripts, which these things are called, need to be executable. So there's a permission that you need to set on the text file to make it executable, to allow the system to run it, to allow the built-in interpreter to actually go in and interpret that. And that's part of setting the proper permissions. And pretty much all modern operating systems have some type of scripting language built into it. Under Linux, it's the Linux shell, the bash shell. That's what this code is right here. Under Windows, we have a couple. I mean, there's the old Windows batch file from the regular Windows CLI, but in more recent years, there's the Windows PowerShell, which is a specifically designed scripting language for Windows to allow administrators to automate common tasks that they don't want be forced to go through the GUIs to use every time. And I mentioned it before, interpreted languages like Perl are technically scripts because they're interpreted. So what does this actually look like? If this is something we're going to be doing, can we see it? Certainly. We can totally take a look at it. Here is a PuTTY window and a secure shell window into one of my Linux servers. And I'm sitting here at a command prompt, right? And if you notice, I'm sitting here, I'm logged in as root, the administrative user, and I'm sitting under root's home directory. And if I go in and look at the contents of root's home directory, I see a couple of things here. And these actually may not be terribly visible in the video. But I've got 3 files on here, and they're in green text. And under this particular program, green text means executable. So these scripts have already been written and they've been set to be executable. Compare that to like these log files, right? Which use black text. That means they're just straight text files. They're nothing. The RPM here, the red one, that's a binary file. So let's go ahead and take a look at one here. I cracked open one of these text files, one of these shell scripts called test1. And it's just a little simple hello world script. Right? Not a lot to it. This first line that starts a script, that's called the shebang line. And what that does is it tells the command interpreter which language am I using. Because there's many different Linux shells. Right now we're using the bash shell. We're saying the bash shell under the directory bin bash. That stands for born again shell. That is it's a descendant of the original born shell, hence a little play on words there. And a very, very, very common Unix shell. By far not the only one. We've got other shells. We've got C shell, TC shell, Z shell, corn shell, you name it. And they all have different syntaxes. So the first line has to tell the interpreter, hey, what syntax am I going to be speaking? The next line, well, enters a clear command. It clears a screen. Echoes or prints the phrase hello world to the screen, and then just exit the program. So maybe not very practical, but at least it is indeed simple. What does it look like when we run it? Whoops. Helps if I spell it correctly. There we go. It just did exactly what it said it would. Cleared the screen, printed hello world to the terminal, and exited the program. So there we are. Hey, hello world programs, they're great for demos, but they're not terribly useful, are they? Let's take a look at a potentially more useful shell script. This is a script called FTP user add. Well, that sounds interesting. Let's take a look at that. This is actually a script that I wrote for a customer a couple of years ago who had a Linux SFTP server and had the need to be able to readily add and remove SFTP users from that system. So I went and wrote this little script to do it because it is indeed a very error-intensive process if you're doing this a lot. The script's longer, but it's still pretty simple, right? And the stuff is still that we earlier discussed is still there. Line 1, there's our shebang line. So we're telling the interpreter, hey, use bash for this. Now under bash, anything that starts with a hashtag or # is considered a comment. And it's considered good form to comment your code, right? For no other reason, so when you go back to it 2 years later, it helps you remember what you were thinking. Or if somebody else has to go back in and manage your code after either you're on vacation, you've moved to another job, whatever, it allows them to be able to figure out what you were trying to do. So comments, they're good. I have a little if-then statement right here to check to see if you're the root user. Right? Because if you're not root, you don't have permissions to add users. And then we go into the main part of the script. Clears the screen, a little banner that prints at the beginning of the program. And then on this program, you manually type in the usernames. So it prompts for the user or the admin to type in the name of the user, right? And then it reads it, assigns it to a variable, does another little if-then statement to see if it's a duplicate, because you don't want to have two users with the same name. That'll cause confusion. Scroll down here a bit. And you can nest programming constructs. So within this if-then statement, I have a case select statement. That's a manner for which the code can look at different decisions or different choices that are handed back to it and do things based on that. In this case, it's asking the person running the program, hey, this user already exists. Do you want to delete them? Yes or no? And if the person types in yes, it goes through and deletes that existing user. And if it types in no, it just exits the program. All right. Then we've got other parts here. We verified the users. Is this really the person you want to put in? Yes or no? Here's another case select. If you tell it yes, then it goes through and actually runs the commands to create that user. And these are just shell commands. These are commands that we would normally type from the command line if we were doing this manually. It's just that the script does it for us. And we're making use of things like variables, right? And of course, if you're the person selects, no, I don't actually want to add this user, then it just exits the program. So a very, very common type of shell script, and one that you're likely going to end up creating, if not specifically for Bash or not specifically for Linux, for whatever operating system you're going to be working in. And that, like we say in Hollywood, is a wrap. So we didn't learn how to program. No, 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 no. But we talked about what programming was. And we looked at the different types. We looked at high-level languages versus low-level languages versus interpreted versus compiled versus structured versus object-oriented. This is fun stuff, and if you stay with the CMIT program, there are courses that you'll be able to take, both required courses and electives, right, up in the computer science department for Java and C++ or whatever. So I strongly encourage you, go out, learn this stuff, practice it. It's fun. And that is going to wrap us for this week. You have a good week, and I will see you next week.